Hi and welcome to this first video on Bernoulli distributions and binomial probability. And I'm going to be running through this across a series of videos. I don't know quite how many videos it will take yet, but I will chop it up into good bite-sized pieces for you. In this series of videos though, you'll be learning all about how to calculate probabilities based on binomial situations by considering Bernoulli distributions. So when we say binomial situations, we're talking about a situation with two possible outcomes. So an event with two possible outcomes, if you roll a dice, for example, that has 6 possible outcomes, but we can make it binomial by saying, well, what are the chances of getting a 5 or not getting a 5, and then you've just got the two possible outcomes. Or what are the chances of getting an odd or an even, for example. Flipping a coin is obviously the classic two outcome event that might also be considered. So there's some learning goals and success criteria for you, and also the resources from the textbook that we're using, Cambridge. And let's roll on now. So imagine I roll a dice and I'm interested in the number of 5s I get in 3 rolls. We're going to complete this table where I could get, there's 3 rolls, so I could get 3 5s, 2 5s, 1 5, or no 5s of course. And if I set this up, this is to start with definitely the long way, but I could set up a tree diagram for this. Okay, so here's my tree diagram, and I'll just put a 0 here, and you can see that I've set this up first of all neatly, and I've done this by just putting each event down a vertical line here. So if you're drawing a tree diagram, just be considerate of how you can be neat. But secondly, I've set this up so that we've got our 8 obvious outcomes, and I've drawn the probabilities on the first 2 branches only. These events are independent. So what I mean by that is that getting a 5 in the second roll, well, it doesn't change depending on what I got in the first roll. So we're assuming that this dice is independent and won't be affected by previous rolls. And I've chosen colors there to show you the number of 5s that occur based on this, this series of events. So this is like the discrete probability distribution that we're doing in the previous lessons. Now, if I move along these branches, I can calculate probabilities. So for example, my orange one here, the probability of getting 3 5s, so that is the probability that x equals 3, is equal to 1/6, that's the first 5, times 1/6, that's the second 5, times 1/6, which is the third 5, giving me a total probability of, so that's not on top, 1 out of 216. So that's of getting 3 5s. Now in green, I get the probability of getting 2 5s. Probability that x is equal to 2. And that's equal to 1/6 for the first 5, times 1/6 for the second 5, times 5/6 of getting a third not 5. But of course this has happened 1, 2, 3 times. And if we float along the branches, we'll see it's 1/6, 1/6, 5/6. And the second option is 1/6, 5/6, 1/6, which is exactly the same because it doesn't matter which order I multiply in. The third option is 5/6, 1/6, 1/6, the same again. So I actually get times 3 because there are 3 ways of doing it. And you'll recognize that 3, that comes up in our binomial expansion that we previously did. And so I get 15 over 216. And then I've got my purple one. And my purple one is the probability that x, or the number of 5s I get, is 1. And that's equal to 1/6 times by 5/6 times by 5/6. And again, there are 3 ways of doing it. So multiply by 3. And that's 75 over 216. And then I've got this light blue one. The probability that x is equal to 0 is equal to 5/6 times 5/6 times 5/6, which is equal to 125 over 216. And if we have a close look here, we'll see that 1 plus 15 plus 75 is 91, plus 125 is 216 out of 216. So the probabilities all add up to 1, which is what we expect. So let's just fill this table out now. So the probability of getting 3 is 1 out of 216, 2 is 15 out of 216, 1 is 75 out of 216, and 0 is 125. out of 216. And we expect this as well. We expect 0 or 1 to be about the most likely outcome. If I roll the dice 3 times, I'm not really expecting to get 2 or 3 5s, but I might do. And so there's a small probability of that. So there's our table of rolling the dice. What we're going to do in this topic is look at how we can do all of this working a lot quicker, and how we can use mathematical generalizations to help us with that. So let's move forward. This event, this is a bit of a summary. This event is called a Bernoulli sequence. Each event has 2 possible outcomes, and we are going to typically define them as success or failure. Each event is independent. That is, the probability of success equals P for all. In all cases, it's event 2, event 3, etc. If you repeat a trial n times, then you can count your successes, and so that means that it is a discrete distribution. And our norms are here. Our norms are that the probability of success we call P, the probability of failure we call Q, and Q is equal to 1 minus P in all cases.